Hello, in this video we'll be talking about the derivative function. So recall in our earlier videos we considered the derivative of a function f at a point. We first specified a specific point a, an x value, x equals a, for some fixed value of a. Then the derivative of f at a, in other words f prime of a, turned out to be a specific number. Now of course that number had a graphical and contextual meaning. It's the limit of a difference quotient centered at that point. It's the slope of the tangent line to the curve at that point. And it's the instantaneous rate of change in the function at that point. But ultimately, it is a specific real number. So what happens if we change to a different value of a? If the derivative is still defined, we get a potentially different value for f prime at a. So let's look at an example here. And so here's our good old friend y equals x squared graphed in the purple graph. And I can change a by the slider here. And we can see for different values of a, we get a point a f of a, which is right here. And you can see what its coordinates are at the moment. And then we have a tangent line, and the slope of that tangent line is f prime of a. So at the moment, a is negative 2.6. f of a is 6.76, at least approximately. F prime of a is negative 5.2, the slope of the orange tangent line. Now what happens when I change a, and I move a little bit to the right? Now I get a new point on the graph. I get a new slope for that tangent line. Now the slope is negative 4.2, so a new slope. Now I'll move it a little bit. At negative 2, 4 is the point on the graph when a is negative 2, y is 4, and the slope is negative 4. And notice these slopes are negative, but notice they're getting closer to 0. Negative 3.8 is the slope. Put in an a of negative 1.8, and the derivative process produces a slope, a number, a derivative of negative 3.6. Notice what's happening here. Every time I put in a different a, I get, if it's differentiable there, I get a single number out for the derivative. But that single number is different depending on which number I put in. Where have we seen this before? You put in a certain number, a, and you get out a certain number, f prime of a. Every input gives you exactly one output. We have a name for that. We have a name for things that input-output pairs, where the every input gives you exactly one output. Do you remember that from your algebra class? It's called a function. And so this actually generates a new function. So if we wrote down these ordered pairs, not the ordered pairs in blue here, negative 2, 4, if we wrote down those ordered pairs, that would be the table for the actual function f of x. But if we wrote down the ordered pairs with this a value, which is x value, and the f prime value, for example, if we wrote down the point negative 2, negative 4, which is where we are now, a is negative 2 or x is negative 2, and the f prime is negative 4, that would be a point on a new function derived from the old function, which we call the derivative function. And we can see we get different values here. For example, right at the origin, the tangent line is horizontal, so the derivative is 0. When we go to the right of that, now we start getting some positive tangents. And so I can list off some points in the table of this derivative function. Negative 2.4, negative 4.8. Negative 2.3, negative 4.6. Negative 2.2, negative 4.4. Negative 2.1, negative 4.2. Negative 2, negative 4. Negative 1, negative 2. 0, 0. 1, here we go, 1, 2. 1.5, 3. 2, 4. And so forth. We can generate a table. In fact, here are some of the values for that table. I went down too far. Let's go back up to where we are. Okay, I went way too far down. Okay, so here we are. Here's that specific function, and the function is y equals f of x. So the first line gives you x values. The second line gives you the y values, or output values, of the original function f of x. So notice that we square the x's, we get the y's here. Negative 3 squared is 9, negative 2 squared is 4, negative 1 squared is 1. And so that tells us that these points, negative 3, 9, negative 2, 4, negative 1, 1, 0, 0, those are points on the purple graph, the y equals x squared graph. But if we look at the slope at that point, negative 3, 9, is the slope negative 6. And the slope at the point negative 2, 4 is the slope negative 4. We just saw that on the what we did before. And you can see that in this series of pictures here as well, which are still shots from the GeoGebra sketch. Now, look what we have here. This generates x's and y's for the f prime function. Negative 3, negative 6 will be a point in the table on the graph of the derivative function. Negative 2, negative 4 is a point on that. Negative 1, negative 2, 0, 0, 1, 2, 2, 4, 3, 6, 4, 8. Those are points on that. In fact, you might see a pattern here. I bet you could even tell me what the formula is for f prime of x. Look at the x's, look at the y's here. Do you see a relationship? Okay, the x's are the top line. The same x's for f or f of x, f prime of x. But the y's this time are going to be f prime of x. What would be the formula for f prime of x? Well, I think you can see that they're just twice as much as the x's, so the formula for f prime of x looks like it will be 2x. We can actually prove that in a minute. So the new function is called the derivative function, or simply the derivative of the original function. So now I say f prime of x, which can be written as df over dx, or d over dx of f of x, is the limit as h goes to 0 of f of x plus h minus f of x over h. Exactly the same thing we had before, except I've replaced a by x, because now I'm thinking of this x not as a specific number a, but as a variable. It's a variable that doesn't change as h changes, but it does produce an output here, which is a formula, a table, a whole table of x and y values, a whole graph of those points, a formula that generates that. So in this case, the formula that it generates is the formula y equals f prime of x equals 2x, or y equals 2x, when the original function is y equals x squared, or f of x equals x squared. And again, we'll use the prime to distinguish that from the original function. Now here's a situation where Leibniz notation is more convenient. Look at this right here. The first line says this: when f of x equals x squared, f prime of x equals 2x. Or in other words, f of x equals x squared implies that f prime of x equals 2x. Another way to say exactly the same thing that it takes that entire line to say using Newtonian notation is to use Leibniz notation, which says the derivative of x squared is 2x. And that's all written in that second line. So now you can see an example why we would rather have Leibniz notation in some cases. So remember, the d over dx means take the derivative of, and this says if we take the derivative of x squared, we get 2x. So that's nice. And sometimes we can call this d over dx what's called a differential operator. And in fact, you can think of that differential operator, d over dx, as being a function itself. It accepts an input, which is the function y equals x squared, and it outputs a derivative function, which is the function y equals 2x in this case. So and then it accepts all kinds of functions as inputs and outputs their derivatives. Of course, these functions are functions of a real variable. Okay, so now we can think of the derivative, and not only derivative of point, which is a number, but the derivative of a function, which gives us an entirely new derivative function. Okay, let's take a look at something here. Suppose I have so we said, let's write this one again, y equals x squared, the one we've already just looked at, and then we said y equals 2x is the derivative function. Let's see if this makes sense. Notice that when the original function is decreasing, the derivative is negative. When the original function is increasing, the derivative is positive. The derivative is 0 whenever the original function has a horizontal tangent line, which is at the minimum there. Notice that this turns out to be the derivative here. We can graph some points. So we're saying the derivative right here at 1, when x is 1, the derivative is 2, so that's a point on that graph, and so forth. And so we can look at derivatives that way. So it gives us a new function altogether which we can actually graph.